Hello, everyone. As you mentioned, I'm going to show you a little bit about what we've been doing with EXPRES. I heard from somebody already at the conference that they hadn't seen anything that we've done, so we've been a little too quiet. We've been, for those of you who don't know what EXPRES is, of course, it's on the 4.3 meter telescope, the Lowell Discovery Telescope, formerly the DCT. It's got a resolution of about 137,000. It's fiber-fed, double scrambled, laser frequency comb from Menlo Systems for the calibration. And we've actually been on sky since January of 2018. And we've been doing science observations since somewhere between February and June of 2019, but I'll show you a little later. August 2019 is where we've been doing the 100 Earth survey. This is baby pictures during commissioning with Ryan for scale there. Lily tells me she likes to say that Ryan is a little below average in height. So of course, now this is not only sealed and in vacuum and has been since we closed it up at the end of the commissioning, but it's wrapped in insulation to try and slow the thermal changes. In addition to using LDT, Joe Lama has put on the Lowell Observatory Solar Telescope, LOST, which I looked up this morning, and at high resolution, there's more than, or pardon me, at high signal to noise, there's more than 57,000 spectra of the sun over the last 3 years. So, and Lily and Joe have been working on publishing those observations and how we're doing with that. And I'll show you a little bit about that later as well. So of course, the instrument needs a purpose, and ours is illustrated here in the difference between the transit detections on the right and the radio velocity detections on the left. The region there shaded is the region that we're targeting with EXPRES, particularly past that vertical line at 40 days, where we think that we can really contribute small-ish planets on these longer orbits that clearly exist, pardon me, that don't exist in either the transit or the radio velocity detections. So the 100 Earth survey has been observing since, I say June here, but August really of 2019. We've tried for really high cadence, 20 to 25 nights a semester. Starting this year, that dropped down a little bit to only about 15 nights per semester. We've been dividing those into quarter and sometimes even eighth nights. We do go for a constant signal to noise ratio per target. And there's about 60 targets. These were published in my 2020 paper so that the list is available. Our single measurement precision is around 30 centimeters per second with a nightly bin precision of about 20 centimeters per second. Some targets we do 2 and others 3 observations per night. And I wanted to say something more about that and I can't remember at the moment. So I'll start showing you a few of the results. So one of the first papers that we had was the Mascaro 2b planet atmosphere study, where we found iron 2 lines in the atmosphere of Mascaro 2b. And this was back in 2020. And that's the same year that I went ahead and published the HD 3651 paper showing that an easier way to try and calibrate our instruments was look for stars which had known planets that would clear out any anterior signals that might confuse us, since we were trying to look at RV precisions that were quite a bit lower than what we'd previously gotten. Now, I show this paper from, pardon me, show this plot from the paper, but we've of course had more time to look at this. The activity over time has worsened our fit. We've now got 3 years worth of observations. The RMS is about 94 centimeters per second. so not quite as good. And we're still looking at determining, looking at ways where we can try and mitigate these stellar noise signals. Sam Cabot looked at an active star to try and figure out how Gaussian processes could help us in getting rid of some of these stellar signals. And at the cadences that we're doing, which are in the lower right there for this star, 101501, you can see that it's not doing so great at the cadences that we were doing. So it requires really high cadence in order to remove the stellar activity signals and actually pick up the real signals in the star. Rachel Rotenbacher, who is giving talk here on this on Wednesday, is combining photometry and interferometry of the star with the radial velocity measurements in order to try and get at this, the radial velocity signals as opposed to the spot signals and other activity, and had great success in lowering the stellar noise. Lily Zhao has been working on the EXPRES stellar signals project, which I know many of you have actually been a part of. And one of the takeaways from this, and Lily will be continuing to, or talking about the continuation of the EXPRES stellar signals project also on Wednesday, was that although each of the groups were typically able to reduce the stellar noise, they didn't all agree upon what was noise and what was signal. And so I think that there's still quite a bit of work to do, and Lily will tell you more about that on Wednesday. One more, a much more recent result has actually been the Rosser-McLaughlin measurement for 55 Cancri E, where we see a 42 centimeter per second signal for the Rosser-McLaughlin effect. And this is a fantastic measurement that had been attempted before, and the precision hadn't really been there to see this. So we were really happy to see this nice clean signal. And also is demonstrating the precision that we could get, at least on short term, with EXPRES. So on longer terms, I figured I'd show a selection of our quietest stars from the sample of 60. So here, our quietest star, which doesn't quite have as long a time baseline as the others, 157347, has an RMS of only 62 centimeters per second, with an intranight scatter of only 21 centimeters per second. So consecutive observations of the star over all those nights is really superb, and actually hitting what we expect for our uncertainties. You can see the intranight scatter on all of these is actually quite low, between that 21 and 36 centimeters per second. And with these, we've got all of them at or below about 1 meter per second. So if you assume that none of these stars have any planets, that's still quite quiet. But of course, we expect that most of these will have planets. And here is one of those quiet stars. So this isn't quite ready for publication. We think we need more data to really nail down this system. But we see signals that look like 92 and 42 centimeters per second. For one that's closer to publication, in fact, this is already in review. This is a system that some of you will probably recognize. This is Rho Corona Borealis, where we found the first two planets, the one from 1997 and BJ's from 2016, along with two additional planets, an 18 Earth mass planet on a 280-ish day orbit, and 4 Earth mass planet down in a 13-day orbit, interior to the Jupiter. So this is really exciting and should be out in soon. And then finally, I mentioned early on the solar telescope, and Joe Lama will be talking more about this on Wednesday. And here is a selection of the solar data. The rejected points here are from weather. So these didn't meet the requisite signal to noise cut and were dropped. And so you can see that we're getting a pretty nice, tight daily average. And I'll let Joe fill you in more on that on Wednesday. And so we've now got 3.5 years of EPRVs from EXPRES with lots of signals. So a lot of our stars actually need additional observations because we are seeing signals in them, yet we don't have the observations. This year has been terrible. I don't know how many else of you have been observing frequently during Q1, but we've had a night or two of good observations. So hopefully that picks up later in the year. And that's about it. Thanks.